With that, I think I can, very happy to introduce our speaker today. It's Julia Knight from the University of Notre Dame, and she will speak about limiting density and free structures. Julia.
Thank you very much. And I'm really honored to be part of this seminar. I enjoyed Ted's talk, the recorded version, very, very much last week. So let me begin by saying something about group presentations. So some people use the term presentation to just mean an isomorphic copy, but I want to think the way the group theorists do about this. So a presentation for a group, it's a set of generators and a set of relators. So we think of the group presented by this set of generators. It's generated by the generating tuple, and the identities on the words in the group are exactly the ones that you can prove from the group axioms, and the identities that say this word in the relator, this word is equal to the identity. So Gromov had asked, what does a typical group look like? And he had in mind finitely presented groups. And he described informally, in terms of limiting density, what it might mean for a typical group to have some property. And he was interested in particular in the property of being hyperbolic. I won't define that, but he claimed that in a limiting density sense, the typical group is hyperbolic. And Olshansky made Gromov's notion of limiting density precise, and also gave a precise proof of this fact that the typical group is hyperbolic. So to make the notion precise, there are different ways. And we have to say, what presentations are we going to count? What are the allowable ones? So we'll fix the number of generators, and we'll put conditions on the relators also. So we want to restrict the number of relators. Otherwise, we risk that the typical group is always going to be trivial, or almost always going to be trivial. And we also restrict the form of the relators, but that's in order to make the calculations doable. So Olshansky, in making Gromov's notion precise, did it in the following way. So he fixed the number of generators, fixing the generating tuple, and also fixed the number of relators, and also said those are going to be reduced words. So for a fixed m number of generators and a fixed k the number of relators, he looked at a limiting density notion. And I'll say what that is in just a moment. Kapovich and Shoup did the same thing, but fixing the number of relators at 1. So let me say what the limiting density is. So we've fixed the set of allowable presentations now. We've got a fixed tuple of generators of size m, and we've fixed the number of relators that we're going to allow. And then we could take Q to be some subset of the allowable presentations. And usually it's going to be the set of presentations for which the resulting groups have some interesting property. And then let P sub s be the set of presentations for which the relators all have length at most s. We have k relators maybe, but the relators should have length at most s. This is the set of all of those presentations. And then P sub s of q, that's the set of among those presentations in P sub s that are in the set q. And then the limiting density for q, for this property, is the limit of the number of presentations of, where we bounded the length of the relators by s over the total, provided that limit exists. It may or may not. But this is the limiting density notion that we want to think about. And there's some evidence, there was some evidence that the typical group resembles a free group. So the property of being hyperbolic, that's true of free groups. And there's another property that, so Gromov had claimed that the typical group was hyperbolic, having that property of free groups. And Kapovich and Shoup showed another property. And again, I won't go into details about what this means, but the property they were interested in was saying that the minimal size generating tuples are Nielsen equivalent, which meant that one could be transformed to the other by a finite sequence of really simple steps. You know, like replace one of the elements by its inverse, or reorder them, or well, the third one on these Nielsen steps was replace one element by the result of multiplying it by another. So find a sequence of steps like that would take one basis for a group to another. So this property of the minimal generating tuples are Nielsen equivalent. That's a property of free groups. And I had asked Benjamin Fine, a group theorist. I went to some special session at joint meetings, and Benjamin Fine gave a talk there in which he was talking about elementary first order properties of groups, and telling the group theorists, oh, you need to learn what you can express with elementary first order formulas. And so I asked him about some other property, and I don't remember what it was, asking him whether it held in the limiting density sense. And I knew it was a property of free groups. And Fine just said, oh, in the limiting density sense, all groups look free. So I thought that was an interesting comment, and just offhand. And we can make it precise for properties that can be expressed by elementary first order sentences. So we could identify a sentence with the property of satisfying that sentence, and then state it as a conjecture, at least. Let P consist of the group presentations with, so I'm going to make it M bigger than or equal to 2 generators, and one reduced relators. And the reason I was making it one reduced relator is because the paper I'd read was Kapovich and Shoup, and that's what they were doing. But then the conjecture was for any elementary first order sentence, the limiting density for phi exists. So we're fixing the number of generators, we're fixing the number of relators at 1, and looking at those presentations and saying limiting density should exist for any sentence, and the value of the limiting density should always be 0 or 1. And the value, if the value is 1, the sentence should be true in the non-abelian free groups, and it should be otherwise. And the Sila had shown the reason for this M big 2. So Sila had shown that the elementary first order theory of the free group on M generators is the same for all M bigger than or equal to 2. There's also a series of papers of Karlampovich and Myasnikov with this same thing. So the sentence is true in the free groups. That's a complete theory. So there's some evidence for this conjecture. I talked with Shoup, and he said, "Oh, that seems plausible," and I consider that a piece of evidence. But there's something recent work of Turbo Ho with Coulon and Logan saying for all M bigger than or equal to 2 and K bigger than or equal to 1. So we're fixing the set of allowable presentations in that sense. Also saying that the relators should be reduced in their setting. if an existential sentence has limiting density 1 for one of these fixed M and K, then it's true in the non-abelian free groups. And this is a very deep result. So it involves machinery of, and they're still writing it, the proof of this. But that seems very interesting. I think they also have the converse, but I'm not absolutely certain of this. I think they have, if a sentence is true in the non-abelian free groups, then it's also true in the limiting density sense for any fixed M bigger than or equal to 2 and K bigger than or equal to 1. But in general, the conjecture is still open. And what Johanna and I decided to do, look at simpler settings and generalize the question that Gromov was asking. So we're generalizing it to algebraic varieties. So let me say what that is. So an algebraic language consists of just function symbols, and you could count constants as function symbols. And a variety V is the class of structures for one of these algebraic languages satisfying a set of axioms of a special form. So they're in some sense just identities. So we say for a pair of terms in this algebraic language, T and T prime, that for all X, T equal T prime. Have a set of axioms like that. The group axioms in language for groups do have that form. If you have a function symbol for the inverse and a function symbol for the operation, constant for the identity, the group axioms are of this form. But there are other varieties. And in any variety, there's a good notion of a presentation. So a presentation for a structure in the variety. It has the form, you give a tuple of generators, and you give a set of, not exactly relators, but identities on those generators. So give a finite set, let's say, of identities on the generators. That's the R. And it should have the feature that the identity is true in A. We have a presentation for A. If the identities that are true in A are exactly the ones that are proved from this finite set of identities that we specified R, and the axioms for V. So for an M tuple A, there is a well-defined free structure in the variety. Maybe don't put any identities, or we just say that each AI is equal to itself, or something like that. Something that doesn't really tell us anything we didn't already know. And any member of the variety that's generated by this fixed tuple A is a homomorphic image of the free structure. So it generalizes exactly what we do with groups. And this was looked at, this setting by Maltsev and other people a long time ago. So algebraic varieties were a familiar kind of study in universal algebra. So that's the topic. But we can ask an analog of Gromov's question for an arbitrary variety, algebraic variety. What does a typical member look like? And this it seems to me is an interesting question, and Johanna got interested in it also. So we started thinking about it. Maybe we could do something. And we looked for some specific varieties where we thought maybe we could actually do the calculations, where we understood truth really well. Simpler, we wanted things simpler than the class of groups. We showed some very general lemmas, which would work if we have a variety and we say what are allowable presentations, how many generators and how many identities are we going to allow in our R, and maybe some conditions on those identities. So if we have some setting, some set of allowable presentations in our variety, and we look at a pair of properties, we could say that the union has limiting density 0 if and only if the two properties have limiting density 0. And similarly for any finite union. And the proof is just really easy. When we're counting the number with a certain property over the total allowable of a given, up to a given size on the identities, then that's less than or equal to what we would get when we take the union. And that's less than or equal to what we would get if we added the number where we use the Q1 and the number using the Q2. So that lemma is just, it's true in a very general way. And similarly, something on complements that's true in a very general way. If Q has limiting density 0, if and only if the complementary set of presentations. So we take the set of allowable ones minus Q, that's our QC. And then we can say, well, the sum of the number of presentations in Q and out of Q, where the length was bounded by S over the total, that's got to be the total one. So the first variety that Johanna and I decided to look at was, and this was chosen because it was the simplest we could think of. The language of, it's bijective structures. So the language consists of two unary function symbols, S and S inverse, I'll call them. And the axioms essentially just say that S is a one-to-one function, one-to-one onto. So for all X, S inverse applied to X is X, and S inverse and then X applied to X also gives X. So this just says that we're looking at a one-to-one total function onto. And there's some important sentences that we can isolate the elementary invariants for these things. So every sentence turns out to be equivalent to a Boolean combination of sentences saying there are at least k cycles of size n, where the cycles consist of distinct elements. And sentences beta n, saying that there's a chain of length at least n, where we hadn't gotten any duplicates and any repetitions. And to prove this lemma, saying that these are elementary invariants for structures in the variety, we look at saturated models. So the first case, saying what we want to count as allowable presentations in this variety, this bijective structures. So we considered just one generator and one relator, and so with the one generator, no matter how many relators, the only structures we get, either there's an infinite chain, looks like Z with successor, or we get a finite cycle of some size M, and any element generates the whole. So if we have one generator, this is all we can get, and we could have different sizes for the cycle. But any we might have had a fixed generator, but any other element would have served as a generator. And the truth of the basic sentence is, well, we can figure out which are true. The sentence alpha n k, saying that there are at least k cycles of size n in a one generated structure. For k bigger than 2, this is never going to happen. And for k equal 1, well, it could happen, but there's and the beta n, it's going to happen, saying that there's a chain of length n. It happens in Z, of course, but it also happens in Zm if m is bigger than n. So we can figure out the truth of these sentences easily. And in bijective structures with one generator, we could ignore the invariance beta n because they're really just equivalent to saying you don't have a smaller cycle disjunction of some of the alpha m1s for m less than or equal to n. So then let's put some conditions. We've only mentioned conditions on the number of generators so far, but to say what we want to allow as a presentation for these bijective structures in the first simplest case. So we have let's just say a single identity, and let's also require that the identity have form, a special form to make our calculations easier. We'll put all the function symbols on one side. So we'll say the S and S inverse all occur on the left. And let's put another condition to begin with, that let's require that the identity be reduced, so we don't put S next to S inverse. Okay, so now these are very special class of presentations, but okay, let's see if we can compute with them. So there's now a unique allowable presentation for Z, where we say A equals A, and there are, for each n bigger than or equal to 1, there are exactly 2 of these reduced identities that give us Zn. We could have Sn of A equals A, or we could have Sn minus 1 of A equal A. So these are the left-hand sides of the identity. And the sentences alpha n1 saying that there is a cycle, there is at least one cycle of length n. These have limiting density 0. And because there are only 2 ways this can happen, and there are lots of, after you allow more possibilities, the chances you're going to pick one of those get really small. And the sentences they're false in Z. Well, so in this very limited setting, the conjecture is actually true. We have the basic sentences that matter, the alpha n1s, basic invariants, elementary invariants. So those are true in the free structure Z, just in case they have limiting density 1, and they have limiting density 0. They're false, and that means with those 2 basic lemmas, we get all the Boolean combinations holding the same. So for all sentences phi, the limiting density is 1, if and only if the sentence is true in the free structure Z. It's 0 if it's false in the free structure. So what if the identity is not reduced? We actually get the same result, but there the calculations are a little bit harder. Still, it's doable. We're still thinking just one identity, but we could allow now S inverse, S inverse, so on. And I'll say what are the ingredients of the proof. What do we have to do to show this? When we look at the number of presentations allowable, where this one of these basic sentences alpha, there's a cycle of length n is true. That turns out to involve a sum of combinations, m choose k. So that looked a bit daunting, but then we noticed that the last term in this sum was greater than the sum of all the earlier terms. So we were able to just look at the last term and try to show that with that in the numerator, we got a limiting density of 0. And we used Pascal's identity plus an approximation for 2k choose k, things of that form, where we had to use Stirling's formula for all 3 factorials. But we could get what we wanted then. If we take M generators, still for the bijective structures, and we allow K identities, but still reduced. So I won't put any S next to S inverse. And I'll put the function symbol, it's either all S's or all S inverses. We'll put those on the left. So these are the allowable presentations. And there, when we try to sort of see what can happen, so we could have M copies of Z. Essentially, we just said something like AI equals AI. So the identities don't give us any extra information. But we could also get some number of copies of S. We could get fewer copies of S because some of the AIs are equal to the AJs, or they're located at some number of successor steps away from each other. And so we might have fewer than M copies of Z, or we might have a mix of some copies of Z and some cycles at most M, but possibly fewer. And we would get a copy of, we would get a cycle of length N only if somehow there was a combination of these identities that gave us such a cycle. And in order to get such a cycle, we'd really have to have at least one of our identities has to involve something on the left that an S in an SKAI where the K is less than or equal to N. Or maybe an S minus KAI but the K has to be less than or equal to N. Well, and there are only finitely many of those in total. So what we do to get the result is show that the typical presentation avoids all of these identities, avoids choosing any of them, any of these finitely many, where we have the number of function symbols less than or equal to N. For a specific identity, it's easy to show that the limiting density is 0. Once we get many other choices, we're unlikely to pick that particular one to put in. But then all we're doing is trying to avoid a finite collection of those. And then we use one of those basic lemmas on unions to say we can, the density for the union is also 0. So that's how we get the limiting density for alpha n1 is 0. And then the limiting density for alpha nk is 0 because you can't have at least k many cycles unless you have at least one. So we know those basic invariants. And then the beta n's the limiting density for that turns out to be 1. Essentially because we're avoiding all of these short, the likelihood of getting a short cycle, a cycle less than or equal to length n is 0. Okay, so we know what happens with all of these elementary invariants, but then we know what happens, and what happens agrees with what happens in the free structure. So in the free structure, there are chains of length n for all n, and we don't have any cycles in the free structure. So since the elementary invariants are true in the free structure, if and only if they have density 1, that's true for all sentences. Okay, so again we get the full result. So let's turn to a different variety, abelian groups. So it's closer to all groups, but it's not really all groups. We understand truth. Johanna and I understand truth in the abelian groups better, and even a little bit of calculation seemed more doable there. So the abelian groups do form a variety. All we're doing is adding to the group axioms, the axiom that has the right form. It's saying for all x and for all y, x, y, x inverse, y inverse equals the identity. So that has the right form. And the free abelian group on one generator is, of course, it's the same as the free group on one generator. But on M generators, where the free abelian group is z to the m. So we understand that structure, but we also understand truth in we have elementary invariants. So this goes way back to Shmulevich. Vonda Shmulevich in her thesis arrived at elementary invariants for abelian groups, and she was using elimination of quantifiers to do this, following Tarski, her advisor. And Eckloff and Fisher also gave elementary invariants in a simpler way, using saturation, doing essentially what we did for the bijective structures. And Eckloff and Fisher, I guess, also gave elementary invariants for modules in this same way, in the same paper. So there is a complete set of invariants. So the alpha p and k says for prime p, there are at least k elements divisible by p to the n. And beta p n k says among the set of elements divisible by p to the n, if we quotient out by those divisible by p to the n plus 1, and we can sort of think of that as like a vector space over ZP, and then the dimension of it would be at least K. So when you take an element of ZP and you multiply it by one element in the numerator plus another element of ZP and multiply it by another in the numerator, and the set of choices of these such that you don't, by any of those ZP linear combinations, get something divisible by p to the n plus 1. That's bigger than or equal to k. And there's gamma pnk saying that again, and in the set of elements of order p that are divisible by p to the n has dimension. And this really is a vector space. At least, no, I guess it's not quite a vector. Anyway, the dimension is at least k in the sense linear combinations. And then this delta p and k, saying that now the dimension, now this is a vector space. We're looking in among the elements divisible, the elements of order p, and those divisible by p to the n, and those divisible by p to the n plus 1. And the dimension of the top set over the bottom is at least k. Okay, so there are well-known invariants. And if we fix a setting, a set of allowable presentations for these abelian groups, I'm going to take the one on one generator. And so I'm going to focus just on the sentences saying that there's an element divisible by, where the n is 1, it's essentially just saying this beta pn1 essentially just says that there's an element divisible by p to the n and not by p to the n plus 1. Okay, so that's true in Z. We could take the element p to the n plus 1. Sorry, p to the n. And that it witnesses this. And in the cyclic group on M generators, these are the other things that we could get, taking one generator abelian groups. This sentence beta p n 1 holds if and only if p to the n plus 1 divides m. So we know when it happens. It happens sometimes and not others. So what we can show is that the conjecture actually fails. These sigma 2 sentences that say there's an element divisible by p to the n and not by p to the n plus 1. These are true in Z, the free abelian group on one generator, but the limiting density is not 1. And it's because of these, you divide by 1 over p to the n plus 1, and you get, with more or less equal likelihood, any of the possible remainders. And so this, we get the same thing happening if we have the relator not reduced, if we allow, A inverse next to each other. Again, it's still basically because when we look at the result of dividing by p to the n plus 1, the remainder is 0 with probability the same as any other remainder. So we get same result. Then for two generators, still abelian groups, two generators, a single reduced relator, the sentence beta n1, this is actually going to be true in all. So that sentence doesn't witness the failure of the conjecture, but another sentence does. If we say, well, there are at least two independent elements divisible by p to the n and not by p to the n plus 1, independent over the elements divisible by p to the n plus 1. It's true in Z plus Z, which is the free structure on two generators, free abelian group on two generators. But the limiting density turns out to be 0. There's one other class we looked at, just a little. So we consider the variety of just unary functions. So we put just one function symbol, where for bijective functions, we put in two function symbols. So we have a single function symbol, and we didn't put any axioms on it. So it's just, but it's a variety. And we thought, oh, this looks pretty simple. And we expected it maybe to be like the bijective structures, but maybe we would have to work a little harder to figure out what was going on. But there, well, let's see what could happen just with a single generator and a single identity of the form. No, I think I won't make it. I won't put all the function symbols on one side. So these are the allowable presentations. So some number of iterations of the function. So fn of a equals fm of a. So those are the allowable identities. And the elements of V that we get, if you think about it a little bit, we could just get an omega chain if we had, for example, just A equals A. The M and N were both 0. We could get a finite cycle where we have, for example, Fn A equals A. Or we could get a finite chain leading up to a finite cycle. So we might have that N and M are both bigger than 0. And they're different. And then that would mean that we've got a chain that then is followed by a cycle. The bigger of the M and N, say N is bigger, N minus M chain, and then a cycle. The N minus M cycle, and then the M chain leading to it. So that's all we could get. These are the structures. And the result, so the sentence saying that the function is one-to-one, it's certainly free in the free structure. The free structure is the omega chain. It's also true in the finite cycles, but it's false if we have a finite chain and then a cycle. And it turns out that the sentence saying that the function is one-to-one, it has limiting density 0. We're very likely to get one of these finite chains leading to a finite cycle. Have the M and N both bigger than 0 and different. Well, so Johanna and I feel as if we haven't done a lot, but we got interested in this. And we'd like to know under what conditions, on a variety and on allowable presentations of the conditions of the kind that Olshansky was making for groups. Under what conditions is the conjecture true? Is it the case that for all sentences, elementary first order sentences, the limiting density is 1 if the sentence is true in the free structure and 0 otherwise? So I'll stop there and hope for some discussion.
Great. Thank you very much, Julia, for a great talk. So I think we can open it up to questions with usually. So people are now raising their hands or doing the clap sign, but I guess we can just ask people to unmute themselves and ask a question if they have one, rather than raising their hands using that thing. So please, anyone, if you have a question, go for it. Anybody? Design? Anyone have any questions for Julia? Relatively. Trying to monitor all the different people. Okay, well, if there are no questions, then maybe we'll try to do the breakout sessions.
Well, Damir, there is a hand sign from Luca.
Oh, is there a hand sign? Sorry, that I'm missing.
There is a hand sign from Luca. So if Luca unmutes himself, you can
ask that. Sorry.
Okay. So thanks for the talk. Was great and interesting project. So maybe a naive question. Tell me if I'm wrong, but the varieties you consider for your example should be cases in which for a fixed number of generators, the word problem is solvable. So I was wondering whether you think that maybe just the calculation gets harder when the word problem is unsolvable for that variety, or maybe there is some kind of shift between these two cases, or maybe it's irrelevant. Maybe there is no connection.
Oh, yeah. So I know very little, and actually, that's an interesting question. Of course, in the setting of arbitrary groups, there are plenty with unsolvable word problem, and that does make it maybe more difficult to figure out what's going on. Yeah, Johanna and I have looked at so few examples, and what we were doing was specifically choosing the simplest we could think of in hopes that we could actually carry out all the calculations. I guess one result that I didn't mention of Turbo Ho, so he showed that the typical group satisfies one of infinitely many, the typical group, so fixing the number of generators and the number of relators, maybe fix 2 generators and 1 relator, let's do it that way. The typical group satisfies a one of an infinite collection of existential sentences that are not true in the free group. So none of those sentences is true in the free group. You just essentially say there exist A and B such that A doesn't commute with the existential sentences. A doesn't commute with B, and this word on A and B is equal to the identity. So you take the disjunction of those, and of course those are going to be true most of the time. That is, one or another of them is going to be true most of the time. So that's a reason for considering not infinitary sentences, but finitary. But yeah, it does seem as if understanding what's true in groups, arbitrary groups, is more complicated if you don't know the word problem. You don't know which existential sentences are true in which group.
Okay, thanks.
I could maybe apologize for the fact that there was not really any computability in this talk, and it's supposed to be a computability seminar.
It's computability through an application. So.
There's a slight connection, I suppose, with the limiting density that of the kind that the group theorists looked at. It's the kind that the people doing coarse computing and generic computing also look at, the limiting density. But there they are putting in some computability. So both say we're computability theory people, and we got interested in this.
So I guess there's a question from Sebastian.
Right. So maybe I should switch on my thing. So Julia, just another connection. that might be Bak Kusainov had this notion of a random structure. He explicitly cited also this work of Gromov. So is there any connection
Yes.
there?
So I think what he was doing was something like what you do when you build the random graph.
Right.
There was some probability to the choice of atomic sentences of being true or false. So this isn't quite that. I mean, Turbo Ho gave a talk in our Notre Dame logic seminar a couple of weeks ago, and there he said that this didn't seem to work out for the groups. You know, putting a measure on the groups. That's really what I think Bach was doing, and he said that didn't somehow seem to work. There was a suggestion. So I gave a talk also in our logic seminar on some of the work with Johanna before we knew quite as much as we do now, and it was I guess Anand Pillai had suggested looking at modules, but there it's even for vector spaces over some field, modules over a ring, but vector spaces over a field. It was difficult to think of what's a good measure of length, because you would really only be interested in the atomic sentences that say this, or the identities that say this linear combination is equal to that one, or this linear combination is equal to the identity. And there may be some way to actually put a measure on the ring so that you could get a notion of length. But Johanna and I didn't see how to do that at present.
Thanks.
Any other questions? Should see everybody now if there are hand signs. Okay, so if not, then I guess thank you very much again, Julia, for a great talk.